Hello and welcome to the Badger Talks podcast, the podcast that shares interviews with experts from the University of Wisconsin-Madison community about their work, research, and a little bit about what they're like as people, too. I'm your host, Buzz Kemper. Today, we'll be talking about engineering the next transportation revolution, the rise of electric vehicles. And I'm happy to have as my guest Dr. Mahima Gupta, Assistant Professor with the Department of Electrical and Computer Engineering at the University of Wisconsin-Madison. Mahima, welcome to the show.
Thank you. I'm excited to be here.
Yeah, I want to dive into all this stuff. And I see that you're assistant professor with the Department of Electrical and Computer Engineering at UW-Madison. And you're also affiliated with WEMPEC, which is Wisconsin Electric Machine and Power Electronics Consortium, which sounds kind of steampunky to me. But what is the general basis of your research?
Yes. So within the area of electrical and computer engineering, my focus is on what we call as power and energy systems. Okay. And if we dive a level deeper into it, I work in the area of power electronic systems. Mm-hmm. And what are power electronics, or you may say power conversion systems? I work on designing electronic circuits to convert power from one form to the other. Mm-hmm. If I give one example, let us say in the context of electric vehicles, in an electric vehicle, we have energy storage device, let us say a battery sitting in the car, and then we will have motors that are going to move the vehicle forward. How do we transfer power from, let's say, a battery that may be rated at 400 volts to a motor that may be rated to run at 240 volts, three-phase AC power? So those electronic circuits, how to design them, how to build them, how to make them efficient, power dense is my focus.
Okay. That makes sense. And it also, it makes sense to me as an audio person because we deal with what are called transducers. These microphones we're speaking into, they will take our acoustic energy and turn it into electrical energy that then the computer can comprehend. So I imagine there's some kind of correlation between what that does and what you're working with.
For sure. Absolutely. We can be talking about feedback amplifiers that are linear amplifiers. And now when I'm talking about power conversion, we are looking at power, not amplification, but conversion in some form. And we do share a lot of physics and electrical circuit skill set behind it when we are designing systems like audio amplification and then power conversion circuits.
Okay, makes sense. The topic that we're dealing with mainly today, although I want to get into some side stuff as well, but the main topic we're dealing with is the rise of electric vehicles. And you told me something really interesting before we started rolling, which is that this is actually the second rise of electric vehicles. There was a rise of electric vehicles in, you said 1900?
Yes, that is correct. So,
and I know you're not a historian, but can you give us the basic overview of what was that all about?
Yes, for sure. So if you look back into the history, again, I'm not a historian, but if you look back into the history, if you look at the first electric vehicle that was ever, I would say, invented, it was actually roughly 200 years ago, I think around 1830s by a Scottish inventor.
Early.
Yes.
Wow.
Although that car was not practical, but because it didn't host any rechargeable batteries, we didn't have the technology at that time, but they became more practical in 1880s when battery technology became better. And in fact, because of improvements in battery technology and motor designs came in, in my opinion, the first rise of electric vehicles in 1900s, wherein from what I recall, 1/3 of the vehicles on road in the U.S. were electric.
Wow. And how was the technology? I mean, obviously it wasn't as advanced, but was it a less advanced version of what we have now? In other words, you have a battery, and when the battery gets low, you charge it, and the battery powers a motor. And I mean, was it the same basic concept?
The basic concept was the same, for sure. The technology on how to do it was different in terms of the type of batteries that were used, the type of motors that were used. The range of the electric vehicles was much shorter. From what I think it was around 20 miles or so, because that was good enough at that time.
Yeah, for the time, that's probably about what you're going to get out of your horse and buggy before you have to give your horse a rest. Right?
Yes.
Wow, amazing. So going to the modern day, then we have this amazing rise in the use of EVs, and there are lots of implications for that. And I imagine that some of the factors are environmental, and some of the factors are performance-based, and some of the factors are just the idea that we have vehicles now that can go, 250, 300 miles? What is a typical range now of a modern EV battery?
I would say that's around the right number, based on the size of the vehicle. 250 to 300 miles sounds about average, although there are vehicles that are meant or designed for smaller range and some for higher range as well. But this is a good number. Okay.
So what is the difference in, first of all, I want to deal with efficiency. I imagine an electric motor is going to be a more efficient transfer of power from engine to wheels than a gas engine. Am I correct in that?
Yes, that is. If I just look at motors, which are typically, if I dig a bit deeper, synchronous motors, they can be as high as 99% efficient.
Really?
Yes.
Wow, that's higher than I would have imagined. Okay.
Yes.
Yeah.
And we are getting better and better in designing them. But that is the number that we can reach, although not for all operating ranges, but it is definitely much higher than a gas-powered engine.
And then there is a cost factor, filling a gas tank as opposed to charging a battery. And I know this is a little outside your area, but do you have a comparison of those two things? Is charging a battery half the cost, or 2/3, or 1/3? Or do you know about where that lands?
So if I look at the upfront cost of the electric vehicle, it is definitely higher. And the core reason is the batteries. I would say, so you pay an upfront cost because of the price of the batteries, which is going down rapidly because of federal agencies putting in research funds to make them better and better. So you pay an upfront cost, but if you can recover that cost based on the type of vehicle that you're buying in 7 to 10 years, because like you rightly pointed out, when you pay to charge a vehicle, that is much cheaper than paying for oil, although that depends on the state as well.
Of course, right. Yeah, so now let's get into your research, looking into the specifics of the research that you're doing. How does that apply to electric vehicles? Are you looking at you said you're looking at the transfer of power from a battery to a motor. What are you looking into? What are you finding? And what surprises you? I imagine that's a big suitcase to unpack.
Yes, for sure. So if you look at power electronics converters, I would say based on the applications that we are considering, we want them to be lightweight, we want them to be efficient, we want them to be reliable, we want them to be good electronic citizens when there are so many electronic circuits that are around in their, I would say, environment. If I talk about the context of electric vehicles, some of the main ideas, like you pointed out, highest levels of efficiency that are possible. They have to be good electronic citizens. They are, if we look at the core idea of power electronic circuits, at the heart of it are power semiconductor devices or transistors. They switch, they turn on and they turn off. And with research in power semiconductor devices, they are switching faster and faster. What that means is that if you look at the frequency spectrum of these waveforms, we have a section of, I would say, a section of power contribution that is useful, that leads to power transfer. But we have a whole lot of section of, I would say, harmonics that I would categorize them as, that they don't really lead to any power transfer, but they're just basically energy dissipation in high frequency range.
Okay.
And what that happens is that if you turn on, in fact, I owned an electric vehicle a couple of years ago that was different. And then if I would quickly ramp up my accelerate when I had to go from, let's say, a stop light to an on light, my radio would start to buzz. And
oh, wow.
So you have to make sure that your circuits that you're designing are good electronic citizens, that they don't do things like this, and they have to pass emissions test.
Yes. I love the phrase good electronic citizens because it implies that you have to make them behave.
Yes. And
That's
as we are pushing the limits, making them having the highest efficiency possible, making them power dense so that they're smaller, we get frunk and trunk space, and just doing the best as we can. We are using new semiconductor devices, we are using new circuit topologies, we are using new control algorithms, and that is pushing us to use, say, these new semiconductor devices, and that accelerates problems like these. So there's always, again, no free lunch. So it's a multi-dimensional problem that we're dealing with.
And when you're talking about these circuits switching on and off, what I imagine is, again, in my audio world, we deal in digital audio, which is sentences of zeros and ones.
Yes.
Is there a correlation there? Is that what we're dealing with? Is basically the equivalent of zeros and ones?
That is an excellent point. Exactly that, but several orders of magnitude higher in terms of voltages and currents.
Okay. Yes. That makes sense.
Let's say
right.
a couple of kilowatts, tens of kilowatts, or sometimes even hundreds of kilowatts based on the size of the vehicle that we're talking about,
right,
versus a couple of watts.
Okay, yes. Maggie is not going to get electrocuted by touching the output of our audio computer. That is very good. And she looks happy about that.
For sure.
That is very instructive. And I imagine that your research, people sometimes have this idea of researchers as being, in the ivory tower and, kind of removed from reality, but you used to work for Ford Motor Company.
Yes.
So I imagine that you're dealing with very practical problems and seeking solutions to those problems and working on very specific things. In your research lab, are you working in conjunction with any auto manufacturers now?
So I would say not directly, but indirectly.
Okay, indirectly.
So I'm a part of, I'm like you pointed out in the beginning, I'm affiliated with the Wisconsin Electric Machines and Power Electronics Consortium.
Right.
So that's a research group that is funded by 50 plus industry members, and many automotive companies are a part of that organization.
Oh, okay. Terrific. So that's the connection. All right.
Yes. And we have regular events. One event that I would highlight is an annual review meeting wherein we share our updates, what research we are doing, so that we can take that back to the industry more rapidly, or other way around, the industry can say, oh, this is not what we are I would say worried about. Can you focus on this idea? In fact, just last year, that was my first year as a faculty member, talking about my research at the WEMPEC annual review meeting, and we were working on a power electronic converter design, a new circuit topology that some automotive representatives gave us feedback on, and we directly turned our direction to make it deal with some of the electromagnetic noise issues that I was talking about, and refocus our research to answer that question. Can we actually take this to an electric vehicle and see how this works?
Right. That's the next thing I was going to ask you is, do these auto manufacturers actually approach you and say, here's a problem we're dealing with, or here's an efficiency level that we would like to increase? Do they come to you with specific issues?
So I would say our research is more basic or fundamental with low TRL levels. Okay. So they are thinking 5 years ahead. And then we are thinking 5 years ahead. So So the answer is yes. putting a little bit of context to just add.
No, that's great. I love context. I knew it wouldn't be a simple yes or no, but So can you give me an example of a problem or a challenge that has been presented to you by a manufacturer or by someone in the field, and then you and your team say, let's dig into this?
I can give one recent example. So again, I did give some context in the beginning. When we are talking about power semiconductor devices, the new upcoming devices are called WBG or wide bandgap devices.
Okay.
They can be, instead of silicon carbide or gallium nitride based. They give us high levels of efficiency, high levels of power density. The trade-off is that they turn on and off very fast. So let us say we are switching from 0 volts to 400 volts or 800 volts in tens of nanoseconds. That is considered very fast. What that means is that we have more noise. So if we talk to industry folks from the automotive world or from other worlds, they are using these new devices, but I have not talked to a single person from the industry who say that we are using these devices and switching them fast. They're deliberately slowed down because we are not able to deal with electromagnetic noise issues. What that means, we are not able to be good electronic citizens. So we have to put in filters that leads to efficiency loss that makes our system bigger. So what's the point of using these wide bandgap devices?
Yes. Okay. So we're back to the no free lunch thing. We can solve the problem, but we create another problem or exacerbate another problem. Yeah.
Exactly. So one of the research ideas that I'm working on is the workhorse circuit topology that are used in EVs is called as a voltage source converter. And what we are trying to do is design a new circuit topology that fits into this context of EVs and other applications, but at the same time, at the core of it, do not lead to this much of a noise.
I imagine that you're working on some pretty exciting stuff, but over the next 5 years, you're always looking 5 years ahead.
Yes.
In 5 years from now, what do you think is going to be the biggest advance in electric vehicles from where they are now? What do you think is going to be the thing that's going to be most improved or the most amazing advancement that we will see?
Yes. I'm going to now wear my electrical engineering hat and not my research area. Focus research area hat.
Fair enough.
So I would say we are doing our best trying to design the best power conversion devices that we can with what we have, reaching high top levels of efficiency. Same with the electric machine design experts. I would say the weaker link, in my opinion, would be energy storage devices that are batteries.
The battery. Yeah.
Getting the energy storage levels that we need with the weight that we need and the power levels that we need. They are one of the heaviest components in the, I would say, vehicle design. They are still one of the expensive components in the vehicle design. If we are able to put in the research funds to make them better and better, I think that's going to lead to a faster rise.
Okay. And I'm excited about that because I once went to a computer museum, and the earliest computer that they had at this museum was about the size of, I would say, 6 industrial-sized refrigerators.
Yes.
And the gentleman there who was kind enough to sit and talk to me, have a great conversation with, he told me, I can't remember the number he told me, but I think he said it had 1 or 2% of the computing power of my phone. And so if the batteries go the same way, then we are going to have so much more power in so much smaller and lighter component. I don't know if it'll be exactly analogous, but we've seen this with computers, how the size goes way down and the power goes through the roof.
That's an excellent point. And we have seen that even in power conversion devices. If you look at the power converters that were vacuum tubes from 1920s and 30s that were the size of this room, pretty big for the same power levels.
Yeah.
Right now, if I hold a power converter of that same power level, that would basically be the size of my laptop.
Yeah.
So we have seen that size reduction for sure, dramatic reductions. We just still need to see a little bit more of that in energy storage devices.
Right. Yeah, that's amazing. If someone was being an environmentally conscious person who also wants an efficient form of travel and doesn't, wants to deal with, sort of a minimum of hassles, but wants a good, efficient vehicle that's going to be better for the environment. Do you tell people that today I would recommend an EV over a gas-powered engine?
Well, I do. I myself have a hybrid vehicle.
Excellent.
I was almost about to buy a plug-in vehicle, but at the time, because of where I was living, there was no chargers available.
Right. I have the same
were.
issue. I live in an apartment building
Yes.
and I don't know how I would charge. Yeah.
Yeah, so that is a concern, which is a real concern. Although if you look at the statistics today, there are, from what I remember, again, I'm not a data person, but I think there are about 200,000 public and private charging stations in the country.
Okay.
And it is becoming better and better, particularly with the presence of people are choosing to charge their vehicles overnight. So the motivation is higher and higher. I wish I could see higher levels of motivation, but they are increasing.
Okay, terrific. I gotta say, I feel kind of sorry for anyone who would try to, a salesperson who would try to sell you a car, because they would start out saying, well, ma'am, let me explain. And you'd be saying, dude, hold my beer.
Yes. I can
me.
also give another example. My previous vehicle, I was looking at the numbers. The average price of the vehicle I was purchasing at the time was $25,000.
Yeah.
And when I switched to a hybrid vehicle, it was $30,000, roughly speaking, around 2019. And that was $5,000 to $6,000 more at that time. But if I look at the mileage that I was getting, it was 20 miles per gallon versus 40 miles per gallon.
Okay.
And at the time, that was the decision I made. I was like, that sounds like 100% better miles per gallon.
Yes.
And paying that much less amount of fuel price. I'm like, sure, let's do that, pay that $5,000 up front.
Yeah.
And then just save up on carbon emissions and some charging.
Yeah, terrific. Wow. Just two more quick questions. One is just sort of a cleanup question, which is there anything about EV technology or your research that you would like people to know, but I just haven't asked the right question to get to? What have we not covered that you would like to cover? Well,
I would say that behind all of the work that we do in my research, and then as a part of VEMPEC consortium, as a part of electrical engineering department, is hands-on work. We actually design these converters, we prototype them, we test them, and that is where we learn all the exciting things that we learn about them.
Great.
I would say that is a big part of our experience, and all our students get that experience. And I think that excites them the most, to see what we are imagining in our brains or writing on a piece of paper actually being tested out, I think is very valuable, and you can feel and touch it.
Right. And your research, I should make clear to the listeners that your research is not just confined to electric vehicles. You're dealing with power transfers on all kinds of levels. And so your research and your students could be affecting all kinds of different power systems. Am I correct?
Yes, that is correct. Yeah. We are looking at designing power electronic converter systems for, say, data centers, because of the rising demand of how to deliver power efficiently and in a power-dense manner to these data centers, to looking at how to deliver power to next-generation electric aircrafts, to electric vehicles, again, vehicles on the road. So we are our research is fundamental to the point that some of the work that we do is not touching exactly one application.
Okay.
It could be applied to several different spaces.
Okay. Will we one day be flying on all electric jet airplanes?
I hope so.
Oh, that would be an amazing power. I can't imagine the battery that would be needed to power
yes.
that. That's amazing. And then finally, Mahima, just getting outside your work world, just to get to know you a little bit as a human being. Do you have hobbies, sports? What do you do when you're not involved in the lab?
Well, I love to read. I love to hike.
Okay.
And now I'm a new mother with a 1-year-old infant.
Oh, congratulations. Okay.
So these days it's just going to the university, doing my research, teaching, and going back to take care of my baby.
Yeah,
so
I bet.
Keeping me busy a little bit.
Yeah, I understand. I do not have children, but I understand that they do require some time commitment, yes.
For sure. And it's fun. So.
Yeah, I bet. Do you have a favorite hiking spot?
Oh, that would be Mount Hood in Oregon.
Oh, yes. Okay. Wow. So you've climbed to the summit of Mount Hood?
No, next to it.
Okay.
And just adoring how it looks like.
Oh, wow.
On a nice sunny day is just a beautiful view to see.
I've not climbed much out there, but years ago, an ex-girlfriend of mine asked me if I would climb Mount St. Helens with her. And so I got to climb a volcano, which is amazing because there's no actual summit. There's just a rim. And then if you take one step too many, you're inside the thing. I mean, that was absolutely, absolutely amazing experience. I would love to have 4 more conversations with you about this, but I think we've gone far enough into the weeds. Thank you so much. I learned a lot out of this conversation.
Likewise. Thank you so much for hosting me.
Yes, you're welcome. You've been listening to the Badger Talks podcast. I hope you enjoyed my conversation with Dr. Mahima Gupta, Assistant Professor with the Department of Electrical and Computer Engineering at UW-Madison. Please browse our previous episodes for other topics that may be of interest to you. The Badger Talks podcast is a creation of UW Connects and produced at Audio for the Arts Recording Studio in Madison, Wisconsin. Our music is composed by Bill Purdy and performed by the UW Marching Band. Our engineer is Meggie Shays. I'm Buzz Kemper. Thank you for listening.